All right, now we're going to talk about 10.2. We're going to actually start our hypothesis testing. In Chapter 10, we're doing hypothesis testing on one sample, and in 10.2, we're going to test for population proportion. In 10.3, we will test for population mean. The notation is on the notes, and I'll post these after I filled them out. I'll post them for you to read. The notation P is the population proportion. P naught is the number that we use in H null, the null hypothesis, in order to compare the value that we get to do our hypothesis test. And this is the number from the claim. And then the null hypothesis is always, remember, always, always, always has the equals in it. So this will be that the proportion is equal to the number that is the established value. N is the number of trials, X is the number of successes. So P hat, which is the sample proportion, is made up of X over N, the number of successes out of the number of trials. And you can easily find this on your calculator, but it will also give it to you when you run the test. The critical values come from a Z chart, and we're not going to worry too much about the critical values right now. I don't think you'll need them really for much of anything because that's goes with the classical method, and we're doing the p-value method for testing. So we'll talk about those a little bit later, but right now we're going to kind of skip over them in favor of concentrating on the p-value. The test that we're going to use for this one is under stat and then tests, and it is the one prop Z test, which is number 5. And the test statistic and the p-value come from the calculator, and that's why we're going to skip over this part for right now because it comes from a formula chart that we don't have in our current department formula chart, and we would have to look it up another way. So for now, we're just going to jump over it. Let's look at this example. A marketing manager for a cell phone company claims that more than 35% of all children aged 10 to 11 have cell phones. In a survey of 5,000 children aged 10 to 11, 1,805 of them had cell phones. Test the manager's claim using alpha equals 0.01. So remember that our null hypothesis is going to be, this is a proportion, and it's always going to have the equal in it. And 35%, we write that as a decimal. So that's what we're testing against. That is the status quo, and we're looking to see if there's evidence that that is not true. And the claim is the alternative hypothesis, H1. And so the claim is that more than, so we're going to put the claim is that P is greater than 0.35. This person says it's more than 35%. Alpha is given in the problem, 0.01. And the critical value, again, we're going to skip over that for right now. It requires a table that we don't have easy access to. The test statistic we're going to fill in a minute because the calculator gives us that when we run the test. So as soon as we run the test, we can write that in. The calculator will also draw a picture for us, and we can sketch it in, and then it will give us the p-value, and then we'll make our decision. So the picture is going to be, we're going to shade in an area on here that the calculator will show us, so you'll see what we're talking about. All right, so we're going to go to stat, and we're going to go to tests, and this is number 5, one prop Z test. And I've already put the numbers in, so P naught, the number that we're testing against, is 0.35. And we know that X is 1,805 from the problem, and N is 5,000, so we fill that in. And we're looking at greater than, so this is a right tail test, so we choose the greater than symbol here. And we're going to do calculate first, and then we'll go back and look at draw. So we're going to come down here. You would fill those in as you went. We're going to hit calculate, and it's going to give us this information. Notice that it gives us the test statistic, which is Z. So the test statistic is 1.63. And the p-value is right here. So p equals, and it is 0.0515. When we round to 4 places, it's a probability, so we would round that way. And before we look at our decision, we're going to go back and look at the graph. And we have to kind of start the test over, but the information is already in there, so it's pretty quick. So we're going to clear that and stat. Tests again, 5, and there it is again, but now we're going to come down and we're going to highlight draw and hit enter. And it takes, my calculator's doing this kind of slowly, but it'll do it eventually. It's going to draw a graph and it's going to fill in, shade in the probability area. I guess while it's doing that, we can look at this. Now remember, to reject or not reject has to do with how the p-value compares to alpha. There it goes. So we'll come back and color that in a minute. This is our mean. But remember that our decision is based on how the p-value compares to alpha. And remember, if p is low, O must go. That's our little mnemonic. And so if p is lower than alpha, we reject h naught. In other words, it must go. So we're going to look at the p-value compared to alpha. Alpha was 0, so this is p, and alpha is 0.01. And we can see that 0.0515 is greater than alpha. So p is not low, it's greater than alpha. So if p is not low, then we do not reject. If p is not low, it doesn't have to go. So we keep h naught. The evidence did not support the alternative hypothesis, which was the claim. Remember, this is the claim. And so we do not reject. Now I'm going to go back here since my calculator is finally finished, and I'm going to shade that in. So that's our picture of that's the probability of getting the result that we got. If this is true, that, remember, that's what p is telling us. The probability of getting the test statistic that we got, and the test statistic, it doesn't ask for it, but we can easily find it, is 0.361. And 0.361 is higher than 35%. But remember, this came from a sample, and you're not going to get a sample with exactly 30. You might get a few, but most of the samples are going to have a mean. You've got over 1,800 kids that you sampled, and you're going to have a mean. That's not always going to be right exactly at 35. But this is within the margin of error, even if this is true. So we don't think that the evidence supported this. The evidence did not support this, so we do not reject this. Remember, this is our status quo, and we have to have evidence to reject it, or we don't reject it. So our conclusion is there is not sufficient evidence to support the claim that the percentage of children who have cell phones is higher than 35%. Today it probably is. When this problem was written, it may not have been. So that is how we work that. Like I said, I will take scans of these and post them after I get through this. All right. In the year 2000, 58% of females aged 15 years or older lived alone, according to the U.S. Census Bureau. A sociologist tests whether this percentage is different today by conducting a random sample of 500 females aged 15 years or older and finds that 285 are living alone. Is there sufficient evidence at alpha equals 0.10 to conclude that the proportion has changed since 2000? So remember, our null hypothesis is always, this is still a proportion, always has the equal in it. And here we're going to use 0.58 because that's what this says. And down here, this just says has changed. It doesn't say is more, is less. It just says that it is not equal to that anymore. That's the claim. Alpha is given in the problem as 0.10. And again, we're going to skip the critical value right now since we don't have access to that table easily right here. And the test statistic will be given in the problem. And we'll get a picture. This will be a two-tailed test, so we'll get a picture that has shading at both ends. And all of this other stuff will come when we work the problem. So I'm going to stat test 5. Now I have 0.58. And I have 285 is how many were living alone. And that was out of 500. That was the random sample. So that's our N. This is a two-tail, so it's going to be a not equal here. And first we're going to go to calculate. And we have our test statistic, which is a z-value. And we can see here it's negative 0.45. And we'll get the picture in a minute. The p-value is 0.6505. P-hat, which again, you may not be asked for, but just it's good information. P-hat is 0.57, so that would be 57% in the sample. And we'll come back to our conclusion in our decision and conclusion in just a minute, but let's go back and pick up the picture. So we go back to stat, test 5, come down here to draw. And again, I don't know why my calculator's gotten so slow at drawing this. It used to be a little faster. I guess it's getting older. While we're waiting on it, if we look at the p-value versus alpha, so this is p. Alpha, remember, was 0.10. This is clearly much larger than that. So we have p is greater. P is not low. So we do not reject Ho. So we do not reject. Okay, and you can see the picture, the area of probability is very large when you look at those two areas together. So we've got our mean, and there's a lot of shaded area there. So there is a pretty high probability of getting the sample results that we got, given that the original value is true. So our conclusion is that there is not sufficient evidence to support the claim that the percentage of females 15 or older living alone has changed. And we can put in the original value to make it a little clearer. So there is not sufficient evidence to support the claim that the percentage of females 15 or older living alone has changed from 58%. That's what we have concluded here. Let's look at this one. In 1990, it was reported that 47% of households had a gun. In a survey conducted by the Gallup organization in the year 2000, 395 of 1,012 adults aged 18 years or older said they had a gun in the house. Is there sufficient evidence to support the claim that the proportion of households that have a gun has decreased since 1990? And we'll use alpha equals 0.05. So this is proportion equals, this is 47%, so 0.47. And this is asking, the claim is that it has decreased. So it would look like that. This is a left-tailed test. So again, we'll go in and put that information in number 5. So we have P naught is 0.47. X is 395. N is 1,012. This is left tail, so we're going to go to our lesser than, and we'll go to calculate. P hat, we'll write that down here, is 0.39. Now that was our sample proportion. Our test statistic, Z, is -5.08. We'll get to the picture in a minute. The p-value is 1.9 times 10 to the -7. And remember, that's why we review our scientific notation, so you know what that means. And if we look at it this way, 1, 2, 3, 4, 5, 6, 7. That's the number. So it's a very, very small number. And when we compare that to 0.05, it is definitely less. So P is low. It's lower than alpha. This is alpha. This is P written out. When it kicks into scientific notation, it's generally lower than any of the p-values, any of the alpha values that we're going to be using. If it's smaller than alpha, if it's really small, it's going to kick into scientific notation. So you want to double check that, but it's a good bet that if it has already converted itself into scientific notation in the calculator, it's going to be smaller than most of the alphas that we would use. And we'll look at the picture. So we go back to tests 5, and we're going to go down to draw. And while that does that, if P is low, then we reject H naught. So P is low, we reject hope. And that means that the evidence supported the claim. So there is sufficient evidence to support the claim that the percentage of households with a gun has decreased from 47%. Now, we don't have any way to say what it's decreased to. We only have one sample. Our one sample was 39%, but that's just one sample. But based on that sample and the parameters of the test, we can conclude that it has gone down from 47%. Now, here's a picture. This is a good visual too. Here's the picture. You can't even see the shaded area. It doesn't even show. It is so far out in the tail. It's down here in the left tail, but it's like so far down there, we can't even see it on the picture. So that is a very, very small probability. And what that means is the probability of getting this sample, if this is true, is very small. So our conclusion is that this isn't true any longer. The evidence supports this. That's what we have found there. All right. We're going to look at how to perform a two-tail hypothesis test using a confidence interval, because remember, the confidence interval estimates the parameter, and in this case that would be the proportion, and you can use that to perform a hypothesis test as well. So if we, for instance, on this one, if we're testing the hypothesis that P is equal to 0.12, and the alternative hypothesis is that it is not equal to 0.12, at alpha equals 0.05, if the 95% confidence interval, because this 0.05 and this 0.95, that has to add up to 100. So this would, a 0.05 alpha would correspond to a 95% confidence interval. And if the 95% confidence interval estimate of P is 0.08 to 0.16, what decision would we make? Well, 0.12 is in here. And remember, we can say that with 95% confidence. And 95% confidence leaves the 0.05 alpha. So those go together. And so we would not reject H naught if we did the confidence interval and the value that we were looking at here is in it. We would not reject H naught, because with 95% confidence, the interval says that it very well could be 0.12. It is in the confidence interval. If the 95% confidence interval estimate of P is 0.13 to 0.19, and again, the 95% goes with an alpha of 0.05, then what decision would we make? Well, in this case, we would reject H naught, because 0.12 is not in the confidence interval. And up here, 0.12 is in the confidence interval. You can only do this with a two-tail test. Use the confidence interval as a way to conduct the hypothesis test. It would have to be a two-tail test. And again, you have to use a confidence level that is 1 minus the alpha level. So if you decided to do this test this way, you would have to make sure you use 95% and not some other confidence level. All right, I'll post these notes, and you can look over them when you are completing your homework.